I'm Kevin Haig, and this is the third video update for Group 3. I'm going to tell you a little about the progress we've made in the last couple of weeks, as well as tell you about the design concepts that we decided to go with in implementing our final project. The electrical engineers, Fred, Spencer, and I, we've all been working on the hardware for the robot. We chose to do the gravity design because we think it's going to be the easiest to actually implement and the most effective for the amount of the amount of work we have to put into it. And from what we've seen, it's working out really well so far. We started off, we went to Lowe's and bought some supplies, and brought them back and started working on the base of the robot. We mounted the Lazy Susan and a servo onto the robot, or onto the base, and from there we went on to add the launching arm to the base after some trial and error to figure out the right height and the angles, I guess, that we wanted. And once we mounted that, we figured out the heights that we wanted to drop the ball from to get the different rows. The front and the back row both have one drop height, and then, the middle and the back row both have one height, and then the front row has a separate height that it drops from. The aiming servo, there's two aiming servos. There's one to rotate the Lazy Susan left and right, which lets us choose which column we want to shoot the ball at, and then changing the angle as well as the drop height lets us choose which row we want to shoot into. And we think this method is a lot less complicated than other designs, and we hope it's going to be pretty successful. Using what the TAs taught us in lab on Monday, we went ahead and built a model for our robot that allows us to control both of the PWM servos, which are the two that control the drop height, as well as the feedback control servos, which are the two that control the aiming. We're still waiting on the servo that moves the arm up and down to arrive, but once that gets, actually it got here today, so it's here, we just haven't put that on yet. Once that gets done, then all we'll have to do is mount a counterweight and a mesh to keep the balls from falling out of the loader. So not really too much work to do on the physical robot itself before the demonstration on Monday. The computer engineers have been working on the game logic as well as the image processing, which has been going pretty well as far as I've seen. We've got a pretty good algorithm for determining what's in what cup. They decided to go with the pixel counting method that we learned about in class, which what they do is for the orange and white balls, they determine the red, green, and blue values, and they use that to create a range for each pixel, which they use to tell whether a pixel is orange or white. Then they divide the board into 9 regions, and in each region they determine whether more orange or white pixels there are, and then depending on which one there are, that tells us which ball's in which cup. And then the ball keeps track of the number of pixels of each color in the cup, so then we know if the ball in the cup or on top has changed, which is pretty much all we need to know to see what's in what cup. And for the game logic, we started with a defense first strategy. So the first thing we do is if we see if we're in danger of losing, and of course if we are, we'll block that. Then if we're not in danger of losing, we go for, or we see how many corners we have, and then if we've got 2 corners, we see if we have a winning move that we can take, and if we do, we take that, and then we should win, assuming that our robot is as accurate as we believe it is. Then if we don't have 2 corners, then we go for whichever corner is free until we do have 2 corners. And then if all the corners are full, then we just go for the first open spot. That's pretty much it for this week. I guess we'll finish the robot on Saturday, and then on Monday we'll see how it fares. Bye.